All right, welcome to the next day of notes. Now, I will warn you that with this next topic, it's going to be new, just like a lot of stuff that we've done in PreCal, but give it time and it starts making a lot of sense. So, parametrics, what they're doing is that they're breaking up an equation in terms of a different parameter. And that different parameter we usually call as t. So, the kind of main reason to have parametrics is to graph curves or non-functions using actual functions. So we're going to give you x and y in terms like it might look like a line, it might be a parabola, it might be a trig function, but all of those are functions and we're going to put them together to create a curve or non-function. All right, so let's start off kind of on an easy foot. So here is x in terms of a linear function. So 3t minus 1, its slope, y-intercept, all that. And same thing with y. They're in terms of t. So just to start off, let's see what happens if we pick values of t and try to figure out what x and y are. So I made a table and I just picked some values of t. And usually when we do like functions, we always like to do like -2, -1, 0, 1, and 2. So those are the values of t that I picked. So if you were to plug in -2 into this equation of x, well, you would end up getting -7 out. So it's not just that x is your input and y is your output. In this case, it's our third parameter, time, or t. So in terms of t, if I plug in -2, I get out -7 for x. If I plug in -1, you get -4. If you plug in 0, you get -1, and then 2, and then 5. Same thing happens with y. My input is now t, and I'm picking those values of t. It could have been any values of t. These are just the ones that I chose. And I'm going to get out a y value. So if you plug in -2, you get out -3, then -1, then +1, 3, and then +5. So those are my values. So plugging in this value of t and then getting out an x and y value. Well, when I get an x and y value, I actually get to plot the points using not just in terms of t, but in terms of x and y. So like this point here is the point -7, -3. So you can kind of see I already drew a graph. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, and then there's a point here. So -4, -1 is my next point. So 1, 2, 3, 4, -1, -1, 1, 2, 3, and then 5, 5. Well, if I were to connect those dots, I would end up having a line. So wait a minute, two lines put together form a line? Yes. And again, this is why we're starting off simple to kind of see what it happens. Everybody knows lines. So if I plugged in numbers, I can get out points and all that good stuff. So you're not going to always have to make a table. You are going to end up graphing. And in this case, we're going to eliminate the parameters. So eliminating the parameter means that we're going to eliminate t. We're going to get rid of it and plug it into the other one, kind of like a system of equations. So let's just take this first equation, x equals 3t minus 1, and let's solve that for t. So if I solve that for t, I end up getting x plus 1 all divided by 3, or 1/3 x plus a third, but leave it like this. It makes it simpler. So what I'm going to do is, since I solved for t, I'm going to plug in t into y. So 2t will instead, sorry for the bell, and then plus 1. And then now I'm going to get this into maybe slope-intercept form just to know what it looks like, and it's a little easier to deal with. So what I'm going to do is I'm going to distribute the 2 into there and get 2x plus 2 all over 3, which might be easier to see as 2/3 x plus 2/3 plus 1, which is 1 plus 2/3 is 5/3. So this ends up being the equation where we have a y-intercept of 5/3, which is what, 1 and 2/3, which kind of looks like where I crossed the y-axis there, and a slope of 2/3, which you can see we went up 2 and over 3 for that. So this would be my equation. Now, there is this thing called restrictions based on our values of t. The question is, am I restricted on my values of t to input into here? Well, no, I'm not. So in a line, I can plug in any value of t and get out an x value. There's no restrictions whatsoever. So in this case, since t and x and y end up being any variable, there are no restrictions, and we can say that x and y are elements of the real numbers. Again, by plugging in any value of t, we can even add that to our list. All the values of t can be put in any number for t, and then you can get out an x and y. That's how linear functions work. Well, what about for this next one? Thinking about this idea of restrictions, if I like just looking at this one here, y is 1/2 t. This is another line. So am I restricted on any values of t that I can plug in here? No. If I plug in any value of t, I'm going to get out any y value, and it's going to be part of the real numbers. But what about x equals t squared minus 4? I can still plug in any value of t, but the thing is that there's only so many x values that can come out of here. So if you think about t squared minus 4, if you thought about this like a parabola, it would be a parabola that shifted down 4, opening up. So this was like -4, and your parabola shoots up that way. So in this situation, x cannot be anything less than -4. So here, my restrictions end up being that it's greater than or equal to -4. And we'll talk a little bit more of examples of that. So again, any value of t can be plugged in, but my x's are only going to be those greater than or equal to -4. So instead of making a table here and picking values of t, I'm just going to eliminate the parameter. That means get rid of t. Well, there's one of these equations that's going to be easiest to solve for t, and that's going to be y equals 1/2 t. If I solve that for t, you end up getting 2y. Well, I'm going to kind of do this like system of equations. If I see t in a different equation, I'm going to replace it with 2y. So 2y in place of t minus 4. And this is where a lot of students make mistakes. When you plug in 2y for t, this 2y needs to be in parentheses. There's no ifs, ands, or but about it. It needs to be in parentheses because that changes that coefficient to 4y squared minus 4. Well, if you remember back to conics, this is what a sideways parabola looks like. It opens to the right because y is being squared and x is equal to that. So this is not a function. Now, before we talked about lines and they form a line, but these two functions end up making a non-function here. It's a sideways parabola. So how do we do something like this? Well, this might be just easier to just plug in values. In conics, there's a different way to solve this. So what we can do is we can plug in 0 for x and figure out what y is. So if I plug in 0 for x, I add the 4 over, divide by 4, and we square root that and get plus or minus 1. So that means I have a point at 0, 1, because that's where x is 0. So plugged in 0 for 1, and then -1. So there's 2 points there. Well, what else can I do? Well, I can plug in 0 for y, x equals 4 times 0 squared minus 4, and you end up finding out that that's -4. So 1, 2, 3, 4, point, and all I need is 3 points in order to graph a parabola. You're just going to go that way, and then the other way. And there's my sideways parabola. So this is where parametrics are kind of helping out. So each of these are functions on their own that we're able to graph, but once we put them together, we can create non-functions and kind of see that. Now, where do these restrictions help us out here? Well, in this case, all our x's were greater than or equal to -4. So that doesn't affect anything. Our y's are all real numbers, since it's honestly going to be going all the way more and more up, just increasing very slowly, as well as decreasing on the y's as well. There are times where our restrictions kind of cut off part of the graph, and we'll talk about that here in a little bit. So what we're going to do here is we're going to dive into what we call restrictions and on our parametric equations. And remember that parametric equations is taking apart x's and y's and form t. So when we give you these questions, X, Y, it doesn't matter which one we do, just, we're giving you a trig function or some kind of function in terms of t. So there are a couple of facts that you need to remember. So if you're inputting things into cosine, what comes out? Well, your cosine function is going to be as high as 1 and then go down like less than that, but also it goes down to -1 and everything bigger than that. So this is a fact that you need to remember about cosine as well as sine, is that the output is always between -1 and 1. So we start off with that fact, and that's going to be something that's going to be very helpful along the way. And then from here, since we told you x was cosine of t, I can replace cosine of t with x. And then you just have your inequality that looks like this. And that's your restriction on your x's. So here's another problem where we have x is equal to cosine of t minus 2. So again, what you want to do is you want to start off with your fact that cosine of t is between -1 and 1. Well, then I can't just replace cosine of t with x. I need to get cosine of t minus 2. So what should I do to cosine of t to make it cosine of t minus 2? Well, I subtract 2 from it. Well, if I subtract 2 from that, I have to subtract 2 from every side of the inequality. So this next step you probably don't need to see, but I'm trying to prove kind of a point here, is that when you do this, now I subtracted 2 from both sides, so now cosine of t minus 2 is between -3 and -1. Well, what did we tell you cosine of t minus 2 was? X. And I could say that cosine of t minus 2 was y, and it would be the exact same kind of scenario with your restriction. It would just be your restriction on y instead of your restriction on x. All right, so this next question is kind of a little confusing for some. I'm going to try to use a graphing kind of tool to kind of illustrate what's actually happening here. So cosine on its own, we know the graph for cosine of any input is going to be between -1 and 1. So I already kind of did that on my own in my graphing calculator. This is what cosine looks like, and it's high 1, low -1. And again, it just keeps on going forever. So what happens if I end up squaring that? So what I'm going to do is put cosine in its own parentheses and square it. So this squared kind of goes inside in math, but here we can't do it in the graphing calculator. So let's see, this is going to be my red graph. So, look at that. So if I squared this, all my negative values end up being positive because that's what happens when you square something. And it's not going to get bigger than 1. Like if you square -1, you get +1. So I'll get a lot of students that think, oh, it's just going to be 1. Well, what about like a half? If you square a half, you get a fourth and all that other stuff. So what we end up happening when we square cosine is that it's stuck between 0 and 1. So writing that down, if I square cosine, that's going to be between 0 and 1. Well, cosine squared is our x value here. So we can say the restrictions on x are going to be between 0 and 1. So doing the algebra here is kind of just helping you with your notes. You're not going to always have to do this. If you just remember that cosine squared is between 0 and 1, you don't have to prove that every time. This is now a fact. Like here, what happens if I multiply everything by -2 in cosine squared? Well, you now know that cosine squared of t is always stuck between 0 and 1. So what happens if I manipulate this by multiplying everything by -2? Well, this 0 times -2 gets to be still 0. If you multiply any negative in inequalities, they flip each other. And then we multiply this cosine squared by -2, flip the inequality, and get -2. So since we're talking about this -2 cosine squared being x, and I'm just going to change the order because, I don't know, I'm weird and like my inequalities to always be less than or equal to or just less than. So my restrictions on my x's are going to be between -2 and 0. If you wanted to, you can plug this into the calculator and see how multiplying by -2 makes all our values negative, still like stuck at 0, but ends up going all the way low to -2.
So here's a very important problem that you need to make sure you know how to do. Um, so we have cosine squared, not just cosine. So cosine on its own or sine is between -1 and 1. But if you square those basic trig functions, sine or cosine, like sine squared or cosine squared, the fact of that is that the cosine squared or sine squared is going to be between 0 and 1. So that's where we're going to start. Then you have to ask yourself the question, how do I manipulate this so that it's 2 minus 3 cosine squared? And algebra thinking, you'd think like, okay, well, I add 2 to all the sides and then multiply by -3, but that doesn't quite give you what you need to do. What you actually want to do first is multiply by that coefficient of -3. But remember that with inequalities, when you multiply by negatives, you end up flipping the inequality. So almost forgot that -3. So now -3 cosine squared of t is between 0 and -3. Now I can add 2 to both sides, or all the sides. So you end up getting 2 is greater than or equal to 2 minus 3 cosine squared of t, which is what we're trying to manipulate this to be, is greater than or equal to -1. And again, it doesn't matter what variable we do. We've just been coincidentally using cosine and x. I can use cosine and y, or I can use sine and x, or sine and y. It doesn't matter. I can give you whatever I want to. So therefore, now that I have 2 minus 3 cosine squared of t, which they told us was x, and me being the math person that I am, I always like my inequalities to be less than or equal to, and from least to greatest. So those are my restrictions on x for this problem.
All right. And so now we're going to need to start thinking about our domain situations that you talked about in Algebra 2. So in this case, I need to figure out what values of t work for both of these. Well, in order to square root a number, it has to be 0 or positive on the inside. So for this one here, t could be greater than or equal to 0. For this one here, if I try to get this to be 0 or higher, then t would have to be greater than or equal to -1. So this is a situation where it's an and. This t value has to be the same for both of the equations. So it has to be working for this one and for that one. So which situation, if I ask you to figure out what the and is for these two inequalities, which one would survive? Well, the one that they're both in is t is greater than or equal to 0. So that's going to be my domain restriction for t. I can only plug in t values that are greater than or equal to 0. Well, if you plug in t values that are greater than or equal to 0 into that, well, x ends up also being greater than or equal to 0. Well, what happens if you plug in 0 into this t value? Well, y is going to be 1. And what happens if you plug in any higher values of t? Well, it's just going to be something bigger than 1. So these are my restrictions on x and y. Since t is greater than or equal to 0, I plug that into each of those and find out that x is going to be greater than or equal to 0 and y is going to be greater than or equal to 1. So again, dealing with these, it's going to be easier for you to kind of imagine the graph. Like for secant, for example. Think about secant. Secant were those U-shaped graphs that started at 1 and went up, and started at -1 and went down. So my output for any secant has to be greater than 1 or less than 1, or less than -1. Well, does it actually equal those? Yes. So since x is secant, x is going to be restricted to any x's that are less than -1, and that x is greater than or equal to +1. So it has to work for both of these. So these are your restrictions on x's. It's this and that. I know it's a little weird to kind of put an and in there. You're not looking for the overlap for these, but you're just kind of doing this and that. That's where our x's are going to lie. What about y equals tangent of t? Well, tangent was that, kind of cubic graph that went all the way up and down. If you plugged in any value of tangent, you would end up getting some kind of output. So that means all of our outputs are available for y. So we'll just say that y is an element of the real numbers. Some of y'all are thinking, oh, what about those asymptotes? That's fine. That means we're restricted on our inputs, but honestly, we get any value of y out since we have that kind of cubic looking function that just goes on forever up and down. All right. So what happens if they're squared? Well, if you square any of these kind of secant graphs, it's going to be kind of like what we did with the cosine function earlier. Everything's going to be shifted up. Everything's going to end up being positive. So if secant is less than or equal to -1 or greater than or equal to +1, if I square that, we end up just getting all of our positive values that are greater than or equal to 1. Tangent squared almost kind of does what we do with secant, where if I square everything, it makes it positive, but it still gets kind of broken at 0. So that means we end up having y is greater than or equal to 0. So let's look at a graph. So I didn't just do one period length of tangent, but this is what the tangent graph looks like. It just keeps on going on forever and ever. So let's see what happens if I square that. So again, I'm going to put just this in the calculator just so that y'all can visualize what's happening here. So my red one is going to be the squares of tangent. So look how it goes 0 and up. It ends up looking like a parabola here where that's at 0 and just like goes up. So all of my values are going to be positive, but the smallest possible value it can happen is still 0. Because 0 squared is still 0. So it does take a little bit of practice and a little bit of kind of visualization of these graphs in order to kind of see what our restrictions are. These restrictions are going to limit what my graphs do. So let's look at some examples here. So in this situation, we're dealing with square roots. So am I able to plug in any value of t here? Well, t has to be positive or 0, so t has to be greater than or equal to 0. So we always want to think about our restrictions first. So let's think about our x's first. Well, for negative root t, you have to be very careful here. So what I want to do is kind of think about the graph of this. If it's negative root t, that means that all of our output values are negative. So if I'm plugging any values of t that are greater than or equal to 0, then all of my outputs are going to be negative. So that means my x's are going to be restricted to everything less than or equal to 0. Again, think about the graph. It's helpful. And again, we're not restricted on our values of t, not like what we did before, where this had to be greater than or equal to -1 because the inside had to be 0 or higher. In this case, it doesn't matter. Well, what about this graph here? If you think about the square root function, so we take it, we move it up 2, and then it shoots off to infinity. So that means that our y values are going to be all the numbers that are bigger than or equal to 2. For some of y'all that are more visual, here it is. This is my blue equation of negative root x. Notice that all of my outputs are less than or equal to 0. This red one was a 2 plus root t. So I'm starting off at 2 and shooting off forever. So it starts off at 2 and goes bigger and bigger and bigger. So again, visualizing the graphs are going to be helpful, but these are the restrictions on my x's and y's. Now I need to eliminate the parameter. So I'm going to solve one of these for t, or in this case, root t. So what I'm going to do is I'm going to take x equals negative root t and solve it for just the square root of t. I don't even have to square both sides. Because if I find out that the square root of t is equal to negative x, I can just plug in negative x in for the square root of t. So you can rewrite this as negative x plus 2 if you wanted to. Okay. So that's eliminating my parameter, getting rid of the t and having an equation in terms of x and y. So this is going to be an equation with a y-intercept of 2 and a slope of -1. But notice what our restrictions are. I could draw this whole graph and erase what I don't want, or I can kind of just start plugging in values of x that are less than 0 to make sure that I get out values that are bigger than 2. So what I'm gonna do here is I'm gonna just in pencil kind of have my y-intercept at 2 and then have a slope of -1, 1. and I could just keep on going forever like that. That would be the graph if I didn't have any restrictions on my parameters like I did on that first problem. But here, I need to have all my x's that are less than or equal to 0, which are all those values, and y ends up being greater than or equal to 2. So the only part of my graph that I can actually officially put on my work is this ray that shoots off that way. Because again, this is the only part of this equation where we have x's that are less than or equal to 0 and bigger than or equal to 2. If you were to start off plugging in 0 into here and start plugging in negative values, you'll get this exact same graph. Plug in points. That's what a graphing calculator does, just does it a lot quicker. All right, so what about this next one? So we talked about cosine. Cosine is between -1 and 1. Well, if I'm changing my amplitude to 3, that means this is going to go low -3 and high +3. So that means the restrictions on my x's are all my x's between -3 and 3. And in this case, the same thing happens with the y's. I can plug in any value of t and output any number between -3 and 3 for both x and y. So now I need to eliminate the parameter. The only way to solve these for t is by doing inverse cosine. So I don't want to do that. What I could do is solve each of these for cosine and sine. So like cosine of t equals x over 3. Sine of t is also equal to x over 3. And then I need to kind of figure out what's some relationship between cosine and sine. Is there an equation out there that I have both cosine and sine in it? Well, hopefully you remember the Pythagorean identity where cosine squared of t plus sine squared of t equals 1. And it could be t, theta, x, whatever variable you want. No matter if they're the exact same, then this identity always works. Well, cosine squared of t is the same thing as if I take this cosine of t and square it. So I can replace the cosine with x over 3 and square it. Same thing happens with the sine. I can replace it with y over 3 and square it. So if I square this, you get x squared over 9 plus y squared over 9, which some of y'all might recognize as an ellipse. Or if we multiply both sides by 9, you end up getting kind of the graphing form of a circle. This is, if you thought about this as being an ellipse, this is a uniform ellipse where you're going left and right 3 and up and down 3, which is, in other words, a circle. So on my graph, I'm going to have a circle centered at 0, 0 with a radius of 3 all the way around. So you just go 3 left, 3 right, 3 up, 3 down, and then just draw your circle. And again, this is not a function. A circle is not a function, but cosine and sine are. So what parametrics allows us to do is draw non-functions or curves in terms of actual functions, as long as you eliminate that third parameter, the third variable. Now, let's make sure that we looked at our restrictions. Our restrictions had our x's between -3 and 3, and our y's between -3 and 3. Hey, it's the whole graph. We don't have to actually erase anything. So does all my graphs, like no matter if I graph it based on like the eliminating the parameter, does it always come out to that? Well, not always. Let's see what happens here. So we have x equals the square root of t plus 1. So if I am thinking about my values of t that work out here, this inside has to be greater than or equal to 0. So if you put like t plus 1 to be greater than or equal to 0, you end up finding out that t has to be bigger than or equal to -1. Well, this one here, well, it's a little typed wrong. It should be -1 all on the inside. So if this one we do t minus 1 is greater than or equal to 0, we find out that t has to be bigger than or equal to 1. Well, t has to be the exact same. So this always has to be and. It's not this or that. It has to be both. It's the same variable t. So in this case, if I have t is greater than or equal to -1 and t is greater than 1, which inequality would actually work out? Well, the t is greater than or equal to 1. So that means that if I plug in values of t that are 1 or greater, well, if I plug in 1 here, you end up getting the square root of 2. And then if you plug in numbers bigger than 1 for t, you end up getting numbers that are bigger than root 2. So our restrictions are going to say that x has to be greater than or equal to root 2. Well, what happens if you plug in 1 into this one? Well, you start off at 0 and keep getting bigger and bigger. So the restrictions on x has to be all the numbers greater than or equal to 2, and y has to be greater than or equal to 0. All right, so now it's the idea of eliminating the parameter. So if I take this x equals the square root of t plus 1, well, there's not really a way to get t by itself without squaring both sides. So with the trig equations, it's a big no-no to square both sides, but in this case, there's no way for us to get rid of that. So I'm going to square both sides and end up having t plus 1. So we end up finding out that t is x squared minus 1. So now I'm going to go back and plug that into the other equation. So y equals the square root of x squared minus 1 minus 1. So this x squared minus 1 I replaced t with. Well, in this case, there's nothing outside this parenthesis besides this minus 1. That's not times negative 1, but that's minus 1. So I'm going to combine that to x squared minus 2. And there's no other way for me to get rid of this square root if I don't square both sides. So we end up having y squared equals x squared minus 2. Well, the situation here is that I need to get x and y on the same side. So we end up doing y squared minus x squared equals negative 2. And this ends up being a conic section, but the only way that this is a conic section is if this is equal to 1. So I need to divide this by negative 2, each of those by negative 2. The negative x squared ends up being positive. The y squared changes to negative equals 1. So if you remember from conics, if we have both x and y being squared and they're being subtracted, this is called a hyperbola. Or a hyperbola if it helps you spell it better. So with hyperbolas, we end up having kind of this box that create. So we need to square root the denominators. In this case, it was 2. So if I square root 2, I'm going to go left root 2, right root 2, up root 2, and down root 2. And it creates this box. This box ends up making asymptotes. So with that box, I draw asymptotes that go through the corners of those boxes. And then you have to remember from your conic section in Algebra 2 what this graph looks like. If it's x squared minus y squared, your hyperbola opens like left and right. So you would have like a parabola looking this way and a parabola looking that way. However, based on our restrictions, y has to be greater than or equal to 0, and x has to be greater than or equal to 2. So the only part of the graph that I end up being able to graph is this part here. So again, our normal hyperbola, we end up having kind of two sideways parabola looking things that go that way. And that would be my hyperbola with asymptotes that go here and here. If it was the other way around, if it was y squared minus x squared, they would open up and down. So it takes a lot of practice and to understand what's going on here. This is still using our idea of conics that you were taught in Algebra 2 last year. If you don't know your conics, please let us know. All right, number 4 here, we're going to trig functions. So cosecant, this is something that you need to know as a fact. If we have cosecant, then our output is less than negative 1 and greater than positive 1. So we're going to say that x is less than or equal to negative 1 and x is greater than or equal to positive 1. If we're talking about cotangent or tangent, that's kind of that cubic function looking thing. So in this case, y is going to be greater than or equal to r. So again, we're talking about these same x values, so we're going to use the word and there. I know it's weird to think about inequalities and and, but for parametrics, they're weird functions and stuff like that. So They have their own rules. All right, so let's eliminate the parameter t. Well, again, one way that I can get t by itself is to inverse cosecant both sides, but then plug in cosecant inverse into cotangent. Just don't do that. Is there a relationship between cosecant and cotangent that we have some kind of equation? Well, hopefully you remember from your identities that cosecant squared of t equals to 1 plus cotangent squared of t. Well, that means that if cosecant is x, and this is cosecant squared, I'm going to have x squared by replacing x with cosecant and then squaring it. Same thing happens with the cotangent. I can replace it with y, and that's squared. Well, if this is a conic, they're both being squared, I should have them both on the same side. So I'm going to subtract the y squared over. Well, this is equal to 1, and you can imagine there's a denominator here for each of those that are 1. So that means on my graph, I'm going to go left 1, right 1, up 1, down 1. So this is negative 1, 1, negative 1, 1. And we create a box. And we have asymptotes that go through the corners of those boxes, of that box. So since it's x squared, y squared, we end up having another hyperbola that looks like this. But remember our restrictions. X has to be all the numbers that are less than or equal to negative 1 and greater than or equal to positive 1. And there's no restrictions on my y's, which means that any y value is able to come out. So I actually have the full hyperbola here that always go towards those asymptotes. So with the restrictions, with this like eliminating parameters, we end up having a full hyperbola that's x squared minus y squared. All right, what about this last problem here? So let's think about our restrictions. So any value of t can be plugged in here. So what output do I get if I multiply sine by 2? Well, all the x's that are between negative 2 and 2. Because thinking about the graph, it's amplitude 2, so low negative 2, high positive 2. What happens if I change the amplitude of cosecant? Well, cosecant are those parabolas that start at 1 and go up, negative 1 and go down. So if you change that to by the factor of 3, then that means that it's all my y values that are less than or equal to negative 3 and greater than or equal to positive 3. Because again, we're still talking about the same y values. It's parameters, so they do some weird stuff with inequalities. But these are just my restrictions. So again, we need to eliminate the value of t. So for this problem, I can get what sine by itself is, which is x over 2. I can get cosecant by itself and get y over 3. What do I know about sine and cosecant? Well, what happens if I multiply sine of t by cosecant of t? We end up getting 1. So that means that if I plug in x over 2 for sine and y over 3 for cosecant, well, they're being multiplied. So that's not any kind of conic section. So I could think about this as x, y over 6 equals 1. That still doesn't look right. What about x, y equals 6? Getting closer. What about y equals 6 over x? Hey, that I should know what that is. This is called a rational function. This is where you have, like a vertical and a horizontal asymptote, and you end up having like a curve here and a curve here. These are rational functions. This is something, again, in Algebra 2. So I'm going to draw my graph, and I have to pay attention to my restrictions. X's have to be between negative 2 and 2. So let's see what happens if I plug in negative 2 into here. So negative 2, and then if I plug that in, I end up getting negative 3. So there's a point there. Well, if I pick another value that's in between negative 2 and 2, negative 1 would output negative 6, which kind of works out. If I just keep on going, I can plug in values and it just keeps on going here. Because with rational functions, 6 over x will never be 0, so it kind of has an asymptote there. What happens if I start, well, again, if I plug in 0, I get undefined. What happens if I plug in 1? Well, you end up getting 1, 2, 3, 4, 5, 6. If I plug in 2, the maximum value of x, you end up getting 3. Well, I can't plug in x is 3 because that's not within the range or the output or restrictions. And if you kind of notice, all my y values ended up being less than -3 and greater than or equal to +3. So instead of a full rational function like this, we have pieces of the rational function that look like that. So I bet right now you're a little confused, which is fine. This is what always happens with parametrics, but with practice, you're going to get better at this. So just make sure, try a little bit on the homework, practice kind of the idea of what X and Y are being restricted by, and bring questions to class or bring questions to tutorials. This is kind of challenging, and what's nice is that we'll have time in class to ask questions. So try to get a little bit of practice or bring questions in class. See ya.